This PhysCast is looking at the distance between photons in a low power laser beam. You might like to pause briefly and read through the question carefully. You can see that we're looking at a beam of light here using the model of a stream of photons moving along. So let's draw a little diagram to help us along here. Here's perhaps one photon moving along in one direction. Here's another photon in our laser beam moving along. And we're going under the assumption here, and we'll soon find out if our calculation upholds that assumption, that there is some distance between these photons in our beam. We're told about the average power of our beam here, half a nanowatt. What does it tell us? That tells us that as this light is passing some region of space here, it tells us the power, which is the energy that crosses that part of space there, per unit time, in some time delta t. And we're assuming that that energy is being delivered one photon at a time. It's not a wave continuously depositing that energy, it's coming across one photon at a time. And what we'd like to know is, for this particular power, what is the distance, let's call it d here, between any two photons coming along in our beam. And we know that each of those photons carries energy, and each of those photons will carry an energy equal to Planck's constant times its frequency. But in our problem here, we're actually given a wavelength, so let's write that in terms of Planck's constant times the speed of light divided by wavelength. So we can write using that the power will simply be the energy of a photon, hc divided by lambda, with this delta t here essentially being the time between each of these photons arriving. So rather than that distance, we can think about a time interval between those two. So if we've got hc on lambda's worth of energy arriving every time interval delta t, that's the power that's in that particular beam of light. Now we'd like to know this quantity here, d, rather than delta t. Do we know a relationship between these? And of course we do. We know that these photons always move at the speed of light, and that tells us that the speed of light c will be that distance divided by that time. And we can rearrange that fairly straightforwardly to see that this time interval between our photons is simply going to be the distance between them divided by the speed of light. So we could write down now that our power here will be this hc divided by lambda divided by delta t, but delta t is d over c, so it will be multiplied by c. That'll give us a c squared on top, and then a d on the bottom there. And what we're really after here, we know all these quantities except for the distance between these photons. Let's rearrange that expression here to say that the distance between the photons must be Planck's constant times c squared divided by the wavelength multiplied by the power. And we have values for all of these. Planck's constant, a number that you're probably getting quite familiar with. We'll write that there in SI units. The speed of light, we want that to be squared. So let's do 3 by 10 to the 8 squared, divided by our wavelength, which we're told in nanometers. So again, we need to make sure we're doing everything in SI units. So there's my wavelength in nanometers, and my power here I'm told is half a nanowatt. So let's put that in there as 0.5 by 10 to the minus 9. And if I do all of that calculation there, I wind up with a number here of 0.19. And as I've done everything in SI units, this will be in the SI unit of distance, so that will be in meters. Or we can think about that maybe instead as 19 centimeters. So the distance between our any two photons here in our 0.5 nanowatt beam at 633 nanometer wavelength is almost 20 centimeters. That's a fairly macroscopic distance to think about. So if we were having an experiment where we wanted one photon at a time in an apparatus, we just need to make sure that the dimensions of our apparatus were something, around 20 centimeters or smaller, and then we'd always have only one photon at a time present in our experiment.